Hello, everyone, and welcome to this video on primer and programming. This is the first in a series of lectures for the course Machine Learning and Biotechnology. My name is Ian Hoffecker, and to start things off, why do we want to do programming for machine learning? So this might seem self-evident, but the basis of machine learning, of course, is in code. And so to quote Richard Feynman here, what I cannot create, I do not understand. So if we want to begin to be able to understand machine learning, then we want to be able to build machine learning algorithms from the ground up, and coding is the way to do this. Another reason to get into programming is that it can empower research ideas. So this is an interesting image from a paper where a neural network was implemented at the molecular level. So this is a DNA-based neural network. And this idea stems from the logic of machine learning and programming. But this application is unexpected and interesting research direction that was born out of a deep understanding of the fundamental logic. Freedom, that's another reason. So you can do customized algorithm development if you know how to code. And this means you're not dependent on other softwares that may or may not meet the needs of your particular problem. Often you have to pay to get these solutions, and it can be faster and easier a lot of times to just build things yourself. And then finally, collaboration. So programming has become really the lingua franca in science. If you're reading papers these days, you'll see that interdisciplinarity is very high. People from many different backgrounds come together, but what unites everyone is the language of statistics, mathematics, and increasingly programming these days. So let's start with a very simple program. So let's say we want to compute 2 to the 8th power. And let's make a flowchart for how you might approach this from an algorithmic perspective. So we could start with these two numbers here, the 2 and 8, the base and the exponent. So we can think of these as input parameters for our algorithm. So maybe a user would supply a different set of numbers, and those would get assigned to different to these variables accordingly. So we have my base here, which is getting assigned the value 2, and my exponent here, which is getting assigned 8. And then next we have some initialized variables that we're going to use to compute the final solution. So one of these is the answer, ANS here, that we are going to spit out at the end, and we've initialized it at 1. But the idea here is that this is just a placeholder, and this 1 is going to grow into something else. And then the other variable here is the counter, and the counter we're going to use to keep track of how many iterations we've done. And you'll see why that is going to become important. So we have this decision fork here. And the idea is that these numbers are going to be fed into this decision fork. And we're going to check, is the counter less than my exponent? We have two choices here. If that's false, then we go to the left here. If it's true, we go to the right. And if it's true, we're going to perform some additional computations here. And so the computation we perform in this case is we're going to update the value of ANS. So ANS is going to get multiplied with the value of the base, 2 in this case. And whatever value ANS has currently is going to get overwritten with this new computed value. And then we're going to update the value of the counter. So in the same way, we'll take the current value of whatever the counter is, add 1 to that, and then assign that new number to the counter and overwrite what was there previously. And so this gives us a way to manipulate the initialized variables that we're starting with. And what we're going to do is loop back to this earlier point and check again this decision fork. So this statement here now has another chance to potentially go a different way because now we've changed the variables that are being fed in. So this first round we went through, ANS was 1, we multiplied by 2, so now ANS is 2. Counter has been upped to 1 from 0. So if we look at our decision fork here, we see that the counter is still less than my exponent, right? Because the exponent is 8, and our counter after 1 round through this loop here is just 1. So we're once again going to go down the right path, the true path, and we're going to repeat this calculation. So now we multiply 2 with 2 and get 4, and we once again increment our counter. So instead of 1, it's 2 now. And we just keep doing this. So we loop through a third time, and every time we're going back to this decision fork and asking the same question, is the counter less than the value of the exponent? And so 6 is less than 8, 7 is less than 8, but then at some point we reach a critical stage when actually the counter no longer satisfies this condition. So now 8 is no longer less than 8, right? They're equal. So now we have to go to the left, the false case. And what we want the program to do now is return whatever whatever value ANS has at this stage. And so in this case, if we go back here, ANS is 256. And that turns out to be the answer to this math problem here, 2 to the 8th power. So this is a simple example, but this illustrates a lot of the core components of most programs. So we have some kind of input. Maybe this will be data in some cases, and we have a useful output. So this is the result that we're after. We have a conditional statement, a decision. So this is also typical building block in a lot of programs. And we have some kind of loop or repeated calculation. And we might call this thing altogether a function because it's accepting some sort of input, and then it's transforming that input to produce a useful output. So going into a little bit more detail, so we didn't really talk about what kind of loop we're using here, but in programming, there are two common ones that you'll see a lot. One of these is the for loop. And the idea with the for loop is we explicitly are going to decide how many times we're going through this loop. And the way we're going to do that is by supplying a sequence of numbers. So this could be an initial number plus some endpoint, and an understanding that we're going to increment this number sequentially. So maybe the start point is 0, and we're going to increment some kind of counter. So the iterator, in this case, usually denoted with lowercase I, will increment this by 1 until we hit a condition, and then the loop will end. So this is useful for cases when we know exactly how many times we need to execute a particular calculation. So maybe we have a data array that has 155 elements in it, and we want to perform 155 calculations. In contrast, we have while loops, and so these do not have a fixed specification about the number of times we're going to go through the loop. Instead, what you supply is some sort of condition. And so we have code that's inside the loop that's going to execute, and every time it finishes, it'll go back up to the top and just check if this condition is met. So this is maybe the closest to what we have here. So we have this condition, and we're going to keep going through this loop until this condition is no longer satisfied. And then that brings us to this other element, which is the conditional statement. So a while loop, you could think of as kind of a loop that has a conditional statement built in, but you can also have standalone conditional statements, or if statements are called sometimes. And the idea here is that we're going to execute some block of code, but only if a particular condition is met. So maybe your variable x is less than 0. And if that is true, then you will do this block of code. And if that's not true, then you'll do something else. So we have this here, for example, in this flowchart conditional statement where we're checking is the counter less than my exponent. If yes, then do this. And then the false here would be the else case here, as is usually the syntax in most programming languages. And then finally, functions. So this is the other basic building block of most programs. And the idea with a function is it's a piece of code that you're going to run multiple times, probably. So you've kind of generalized the format in order to accept different parameters. So in the case of this power calculation, we might have decided that this is a useful thing to calculate, not just for 2 to the 8th. So we don't want to just do it once, but we want to automate this question. What if I want to compute 3 to the 9th, for example? So we could simply supply a different set of inputs, and then we would get a useful output by following this algorithm. And so a function is going to have this format, right? You have the name of the function, some input parameters, and going to execute some code, and then in most cases return some useful result. So let's put this into practice and try an exercise in Google Colab. So if you go to Google Drive account and click the menu at the top left there and you go to more, you'll see this option for Google Collaboratory. And if you click this, it will open this interactive coding environment here where you can type in programming code in one of these cells and you can run it with this play button here or hit Shift Enter. And so this is running Python natively. So if you don't do anything, the code that you execute will be assumed to be Python. But if we want to run R code, so in this course, we're doing both Python and R. So if you want to run R, you can do this as well in Colab. You just have to run this line here first. %load underscore ext space rpy2.ipython. And then any R code that you write must be prefaced with this %% here. So using this platform, let's explore the implementation of this simple program here. So one way to do this is using a for loop. So we could write a function here. So as we said, we want to generalize this problem. So we don't want to just solve 2 to the 8th, but we want to solve any base raised to any exponent. So the parameters are going to be these variables here. But when we actually call the function, you'll see that we supply the numbers we're interested in. So if we want to check 2 to the 8th, then we would supply 2 as this my base parameter and 8 as this my exponent parameter. And then the function is going to transform these variables and produce or return the output here, ANS. And you'll see that ANS gets returned at the end, but it's initialized as 1 here in the beginning. So this is the placeholder for the answer. And we've also initialized this counter here as 0. And in the for loop, we said that you're going to specify at the outset the program, the number of iterations that you're going to do, or the sequence of iterations that you're going to do. So in this case, we have this iterator variable here, just the underscore, representing the values of this range that's specified here. So we're going to go from 1 to the exponent plus 1. So that's going to be up to, but not including this value in the case of Python. And we're going to increment 1 by a value of 1 each time. So we're going to start from 1, and then we're going to go to 2, and we're going to go to 3 until we hit my exponent. And each time we perform an iteration, we're going to compute this line here, which is simply ANS times my base. So my base is not changing. That's fed as a user input here. And then ANS will be whatever value it happens to be depending on where you are in the loop. So if you're going through the loop the first time, then ANS is 1. So 1 times my base will be 2 if we're doing 2 to the 8th power here. And then we're going to reassign that to ANS here and then repeat this multiple times. So after you repeat this, say 8 times, the loop will simply end because we've exhausted the range here. And then all that's left is to return whatever value is stored in ANS at that point. And then it works the same way here in R. So we have this iterator. Instead of the underscore, we're using I to represent it. And in this particular case, in this for loop, we're not actually even referencing the iterator for anything. So in many programs, you will use the iterator for something. But in this case, we just want to perform this operation a certain number of times. So we're not actually using I here or underscore here, but it is nevertheless changing according to this range. And then we're computing this ANS update each time and returning it at the end. And you can see if we test out the function here, we would successfully print out the answer 256 for the case of 2 to the 8th power. So for loop is one way to do this, but you can also do this with a while loop. So this is more similar to the flowchart that I showed at the beginning. So in this case, we have a while loop, which is going to go forever until this condition is met. So we haven't specified the number of times we're going through the loop. But what we do have is this counter here, and this counter is going to get updated each time we go through the loop because we have this additional line inside the loop, which is here to increment the counter. So it's going to take whatever value it has at a particular moment, plus 1, and then reassign this new value to the counter. And same thing over here for the R version. And then finally, there's a third way we could do this. So we don't necessarily need to supply the condition at the beginning of the while loop. So we can just create an infinite while loop. So this while true will just keep going forever unless we do something to break the loop. And so that's what we have here. We have a conditional statement, which is going to get set off anytime the counter is greater than or equal to the exponent. And then when that happens, it will execute the code that is indented here underneath the if line. And so that line here is this return ANS. So this will effectively end the function and break the loop and spit out whatever ANS happens to be in that moment. That's a simple example. And then now let's try something a bit more advanced. So I've prepared some pre-configured code. So if you go to this link here, my GitHub page, we have a notebook, which if you open it up, you'll see this button here, open in Colab. And if you click that button, it will open the pre-configured code that we have, and you'll have the option to save your own copy in your own Google Drive. So if you make changes and don't want to lose them, then you'll be able to save them and keep them without altering the master file. And just keep in mind that if you're working in R and not Python, then to run any R, you'll still have to run this line here. So at the beginning of this sheet, one of the first things you'll see is we've made a kind of cheat sheet here for sequential data types, one for Python and one for R. And sequential data types are essential for any situation where you're working with data. So often we'll have some sort of data file, and it will come in the form of a sequence of numbers. And the important thing with these data types, so in the case of Python, we have lists and NumPy arrays, and it's not shown here, but also data frames is the third type. And then on the R side, we have vectors and also lists in R. And the thing these have in common is they're ordered lists. So we have some numbers, but then each of those numbers has a particular position. And this is key because the position is going to give us the ability to access kind of an algorithmic way values that are stored in this data structure. So the index here is just a count. So it's just indicating the order. And an important difference between Python and R is that indexing starts from 0 in the case of Python and starts from 1 in the case of R. So if we look at this example here, we have my list, just created a simple list here, 1, 2, 3, 4, 5 with the square brackets. And then let's say we want to access the 0th item, the first item rather, that's occurring in the list. So in Python, you would do this with my list and in brackets 0. And so that would retrieve whatever is stored at the beginning of the list. And in contrast to that, if we create a vector in R with this syntax here, C parentheses 1, 2, 3, 4, 5, if we want to fetch the item at the beginning of this vector, we would call it with my vector in brackets 1 here. So sequential data types are useful. And so if we want to do a kind of exercise with them, let's imagine we have some data. So here I've just drawn out some arbitrary data here. So imagine we have these measurements, let's say. And what we want to do is organize these into a histogram. So a histogram is a set of bins and counts or frequencies. So the bins here, you'll see I've defined them on the left here. They're defined by a range of values. So bin 1 here is any data that's falling in the range from 0 to 10. Bin 2 here is anything from 10 to 20, and bin 3 here is 20 to 30. And so if we were going to construct a histogram from this, what we would do is go through each of our data points and sort them into these bins. So 3.68 has to go into bin 1 here because it's between 0 and 10. 10.95 here is going to go into bin 2 because it's between 10 and 20. And what we'll do at the end is, or as we go, is keep track of how many of these go into each bin. So if we look at these, we have 4 items here, for example, for bin 2. And the histogram is essentially going to be a list here where the order is corresponding to the bins. So we have bin 1, bin 2, bin 3 here. And the numbers, the values stored in this list are the counts or frequencies, n here. So there are 2 of these values went into the first bin, and 4 went into second bin, and 1 into the last bin. And then these bins may also have a value associated with them. This is X here. So the value of this first bin here, it's representing the range 0 to 10. So to be as accurate as we could, or unassuming, we could say that this bin represents the value 5, because this is going to be the midpoint between the two range values. Likewise, the second bin representing 10 to 20, we could call this bin 15, because it's representing numbers that are more or less close to 15, or between 10 and 20. And this is interesting because we can compute the mean with this data. Okay, it's interesting because we can visualize it, so that's useful. And something interesting that we can do as well is compute the mean. So you're familiar probably with the classic definition of the mean, the arithmetic mean. So we have a sample here, a bunch of data points, and if we want to get the mean, we would of course sum these together. So here this sigma here is representing this summation. So we're going to just sum all the data points and then divide by the total number of data points here. And then that would, of course, give us the mean. But if we have bin data, we have the option to compute the mean and alternative root using a weighted sum. So what we can instead do is multiply the bin values. So these would be, for example, the midpoints or the average values of these bin ranges. And each of those multiplied with the height of the bin. So this product here, we're going to sum this up for as many bins as we happen to have. So in the case where we had 3 bins, we would compute 3 of these products here. And then at the end, again, divide by the total number of data points. And this will also give us the mean, or at least an estimate of the mean here. So this is an exercise. So if we go back to this Colab link that I shared earlier, we have an exercise if you scroll down where I've started some of the code here. So we have a Python version and an R version, and I've created some of the code, but I've left some of it blank here. So the idea is that you're going to fill in the missing portions of this code. And the goal of the exercise is to do what we just did here. So first, to create a histogram by keeping track of the counts and sorting data elements into bins. And then once you have that histogram, to compute the mean using this weighted sum formula. And if you get the answer correctly, it should look like this. So the histogram, we already showed it, has these values 2, 4, and 1. And we have an estimated mean here, approximately 13.5. And you'll note that this is actually different from if we directly calculate the mean from the data. And that's because we're losing some information by just representing these bin values with the midpoint here. So give that a try. So that's a simple example. And then the last thing that I included in this first Colab notebook here is an example of what's to come. So this is really just a preview, and we're not going to go too deeply into it, but I'm just going to kind of show the anatomy of it. And the idea here is to think about it from programming knowledge perspective. So we're not going to think about the machine learning concepts too deeply here, but what's going on is if we run this script that you'll find in the Colab sheet, it will produce this nice plot here. And so what this is actually doing is this is a set of data. So we have some parabolic scattered data here, the blue. And what we're aiming to do is so create a model that is fitting to this data and predicting it. So if I give you an X value, is your model able to predict likely candidate for the Y value that you would have here? So the blue is what we would call training data, and then the red here is our trained model, or the output, the prediction. And so you can run it both in Python, and then there's an R version. And so we just kind of go through the major components here. So at the top of both the R version and the Python version, you'll see a bunch of these import statements. So this is going to be a recurring theme, especially in machine learning, is importing outside modules that have done a lot of the hard work for us. And we're simply going to be calling these modules and utilizing them. And we can do the same in R here. The next section you'll notice is we're utilizing some data. So in this case, we're fetching data from a URL. So we have a link here to GitHub. and a raw data tech.txt file here, data file, is being imported and assigned to this variable df in this case, and also in the R case here. And then this data is then being reshaped and kind of packaged in a format that will be more conducive to us to perform calculations on. So we're assigning part of the data to X and assigning another piece of the data to the Y here. So this will be a common task in a lot of data analysis problems. And then we have some kind of function. And in this case, the function is a neural network that we're using to build this model. And it takes a bunch of parameters like we discussed with other functions. So it works just like any function. It takes these parameters and it's returning a model in this case. So the model is going to be a complex object that has a lot of components to it. But for the most part, this works just like any other function, right? We have inputs, we have outputs, and some code that's going on in between. And that, so yeah, I've explained this a little bit here, but we'll go into this in more detail later in the course. But this neural network, we need to tell it how many layers and nodes and what type of activation function. So this is all terminology that we'll come back to later. So we've defined a function, and then the next step is to run that function. So here we're doing that. So we're assigning to a variable the output of a function that we've now run with this data that we defined 2 slides ago. And then this is another recurring theme. We'll be testing out our models and using them to create predictions that we'll then use to evaluate how well the model is working. And then finally, a common step that we're going to finish off with in almost all cases is some kind of visualization. So in this case, we're producing a plot and we're just comparing the predictions with the data. So presumably, the better the prediction is, the nicer the fit these red dots are going to be with this data. And so that's just preview, and I think it encapsulates what's going to be a recurring theme in this course, which is the idea that machine learning is a kind of function approximation. So we're going to be frequently dealing with a situation where you have some kind of input and some kind of output and a transformation from the input to the output. And this transformation might be a physical process happening in nature that we have absolutely no direct access to. But we nevertheless want to perform this prediction anyway. So machine learning will be often the task of approximating this function in a useful way. So in this case, I literally did generate this data using a Python function here. And so this is, of course, hidden. So if you remember, we imported our data from a URL. So this actually kind of mirrors a common situation. So you might not have access to the function. In this case, as the architect of this data, I do have access. So I was able to generate it. And the goal of the model was to find some approximation of this function without actually having access to it. And so an example of what this could represent is, maybe we have a drug and the Y value here is the outcome. So the patient's, let's say the blood sugar concentration is influenced by the dose of the drug. So we have an input, the amount of the drug, and an output. And we have the data that is representing this process, but the actual function, the physical process that connects the dosage to the patient output is very complex, right? It's biology. And what we want is a model that is going to represent that process as correctly as possible. So that's it for this session and a preview of what's coming next. So the next topic will be a review of probability theory and statistics. So this is the foundation of machine learning. And so some questions to ponder between now and then are what causes statistical variation and what gives a probability distribution its shape? So some deep philosophical questions that can be fun to ponder between now and then. And then next time, we'll tackle the topic of fitting probabilistic models to data. So this is going to be a recurring theme in machine learning. You have some kind of model, and you want to fit it to data. And the technique we'll be using is called the maximum likelihood estimation technique. So that's all. Thank you and goodbye.